go and have just your notes out here, and you have your calculator and your pencil. We're going to do a little bit of practice with things before we eventually get to the homework. I want to talk about some terms that I didn't get a lot of time to dwell on at the end of our last lesson, kind of rushed for time, and the terms accuracy and precision. What are those terms? Talk about accuracy first to me, Kendall, if you would, please. What's accuracy?
It's like how close you are to a value. Like the closest.
Close to what value?
Any value. Or
Not
like
any.
the same value.
Audrey? That wasn't a particularly accurate response. Michael?
The exactness of a measurement.
Good, the exactness, the correctness of a measurement, right? How correct is something? So we gave the example that if Kendall were, let's just say she gained weight. She's 105 pounds today. She was 100 pounds last week. She ate over the weekend. She's 105 pounds, all right? If she's exactly 105 pounds, then an accurate measurement on the scale would be 105 pounds. 104 would be somewhat accurate. 103 would be a little bit accurate. 120 wouldn't be accurate, would it, Kendall? No, not accurate. Accuracy is how exact or how correct is an individual measurement. Now remember, we said when we do our experiments or when we do tests, we do many, many, many trials, right? So each individual measurement will have its own degree of accuracy. Ideally, all the measurements are accurate, right? We want our measurements to be accurate. What is precision then, Kendall?
Like how concise you are.
Not how concise you are. That's if you say very little, like Calvin Coolidge. Audrey?
It's a series of measurements, closeness to each other.
There we go. When you're doing your whole bunch of tests and your whole bunch of measurements, how consistent your results are. How close are they to each other? So Kendall steps on the scale and it says 104. And she steps off and she steps back on again, it says 104. And she steps back off and she steps back on again, and it says 104. All right, the scale is precise. It's at least giving the same reading, but it keeps being just slightly inaccurate, right? Versus she steps on the scale, 105. Steps back on the scale, 110. Okay, she no longer trusts the scale, right? If measurements aren't precise, something's wrong, right? Either the way we're testing it's wrong, the instrument may be flawed, probably the case in the bathroom scale, right? Something's not right. Now, if Kendall is, she steps on the scale and it says one thing, and then she grabs a couple of 5-pound weights and steps on the scale. Well, obviously it's going to read different, right? Or the best part is, you're like, okay, I got to weigh this box to send out to the post office. I wonder how much it weighs. So you step on the bathroom scale, weigh yourself, pick up the box, step on the bathroom scale, and try to read the numbers around the box. Anyone ever done that to try to figure out how much something weighs? I've done that with baby. Like we had a baby scale with our little ones. Lay the baby on the scale. That works for like the first few months of the baby's life. Once the baby can develop the ability to wiggle and roll, the baby scale's out. Okay, it doesn't do anything. But you can't stand the baby on a normal scale. So you weigh yourself, step off, grab baby, step back on, and have spouse read because you can't read the numbers anymore. And then you kind of subtract, right, to get how much baby weighs. Okay, it's whatever. But if you step on, and obviously it's going to read differently if I'm holding baby than it would if I wasn't holding my baby, right? But if you're doing something wrong, your scale might not be precise. If your scale is just jacked up, it may not be precise. You may have uneven flooring. I don't know if that's ever been the case maybe in a bathroom or something where the bathroom scale isn't sitting perfectly level so it doesn't read things quite properly. Or I've heard of these. I've never had a house with this, and I would never have a carpeted bathroom. Can you imagine a carpeted bathroom? No, I don't know. Bad idea. I've seen, you watch those house hunter shows or whatever on HGTV. Okay, yeah, and this is not endorsing house hunters, but and they're like, carpeted bathroom? Yeah, not feeling that one. Gonna rip up that carpet and put down some sort of hard tile surface or something, or laminate, if you're not rich, which we would put laminate, but on HGTV it's always tile, travertine tile, it's extra fancy. Where do you get that money? The house is smaller than mine and it costs 5 times as much. Don't live in Atlanta. Anyway, that's off topic. But accuracy, precision, they're both important, right? If you don't have precision, you can't trust your results. But if they're not accurate, your results are flawed anyway. So who cares that you can trust your results? So accuracy, precision, both important. Again, each individual measurement has its own degree of accuracy. The collection of measurements will have a certain degree of precision, right? And we want to try to get a low variation between the numbers. We think back to Algebra 2 in years past, right? We talked about standard deviation, mean deviation, right? The range should be very, very small. All right, that's precision. Now, what would cause a lack of precision or what would cause a lack of accuracy is a goof up. We call it error. Right? And this was the last thing we had in our notes, was talking about error. And we said there's 2 types of error. One type of error is you're doing it wrong. You're trying to do this test and you're just not doing it the right way. So of course you're going to get error. Or perhaps you're doing these tests and your instrument itself is flawed. Maybe the bathroom scale is just not right. So it can't give you anything but wrong answers. Maybe you thought you were using, maybe in a test or balance or something, you thought you had a 200 gram measurement and you picked up a 100 gram instead. You screwed up, so everything's going to be wrong, right? That type of error caused by a procedure that's wrong, caused by an instrument that's messed up, causing by an instrument that's just not working properly, that type of error is what we call, Michael, systematic error is correct. And other types of error, like just craziness happens, right? You can't always account for everything that's going to go wrong. A door slams right as you're trying to do a very careful measurement, or your glass shatters in the middle of something, and so it messes up the results as little pieces of glass get mixed into the compound or something. And okay, now that throws everything off. Okay, accidents will happen, right? What do we call error that you really can't eliminate because you're not really doing anything wrong, just, life happens. Audrey? Random error. Okay, questions on those types of error. Again, something that we've been talking about at the end of the hour and really kind of rushed it at the end of the last lesson. Any questions? All right. Let's go and talk about something else that we did have plenty of time to cover in the last lesson, and that was significant figures. And with anything we do with numbers, significant figures are an issue. And what we have to be able to do is look at all the numbers that we are given and determine, okay, which of these given numbers are significant and to what degree. Well, first of all, there are some things that are always significant. No question. We don't have to think about it. Kendall? Non-zero digits. If it's a 1 through 9, it's significant. So the only thing we really have to worry about are obviously the zeros. When is a 0 always going to be significant, Audrey?
When it's between numbers.
Right, if it's in between 2 other numbers. So we have a non-zero digit, and at some point there are 0 or zeros, and then there's another non-zero digit after them. If they're in between in any way, those zeros are significant. There are some zeros that are never significant, Michael.
Accurate.
Other one.
Before.
Before. Zeros before a number begin. For instance, 28 could be written 0028. Well, those zeros don't really do anything for me, right? They don't add any special significance. So those zeros are worthless. They do not add any significance. Zeros before, even if it had been a decimal, 0.0028. Well, they are helping me to know that I have thousandths place and 10,000ths place. But other than that, they're not adding anything to the discussion, right? So if they're to the left of a number, or you could say before a number, not significant. And then after a number, sometimes they are. Sometimes they're not. Would these be significant? Yes or no, class?
No.
I'm getting a no. Why not, Kendall?
Because there is no decimal.
There's not a decimal in the number. Now, if it was 28.00, now they're significant. If it was 2,800 point, now they're significant. Or 280.0, or even 2.800, or even 0.2800. If there's a decimal in the number, zeros at the end are significant because they've been put there for a reason to show an exactness or a degree of exactness that exists. All right, but if they're no decimal, no significance. And then there's one other rule that we talked about where there's numbers that can be infinitely significant, meaning we really just ignore them as far as significance goes. Because again, we're always trying to find the least amount of significance and base off of that, or least significant place value, for instance, and base off of that. So when would numbers have infinite significance, in which case we really don't even factor them into the discussion of how should we round our answer? Audrey? Michael? Okay, good. That's actually one of them. Where those aren't so much infinite significance, but they just don't have any effect. So I was getting to that one. I poorly phrased question. But yeah, e-values, powers of 10x scientific notation, right? The times 10 to the whatever or the e whatever, you don't even worry about that. That has nothing to do with significance. That's just showing place value there as well. So good. Okay, so scientific notation doesn't have an impact. But there are other numbers that have infinite significance. Kendall? Numbers obtained by counting or numbers that are used by definition. For instance, in a conversion unit, a mile is 5,280 feet. It's not about 5,280 feet. It is exactly 5,280 feet. That's how we define the mile, right? So because that's how we define the mile, if I were to use the number 5,280 at some point in a calculation, I wouldn't say, only 3 sig figs there, so we're going to round to 3 sig figs in our answer. No, this has no effect on significance whatsoever. It's infinitely significant. It might as well be 5,280.0, and just like infinite number of zeros there, because it's a definition. Or numbers obtained by counting. For instance, we're doing something or other, and we're like, okay, we want 50.0 milliliters in each little test tube, and we're going to have 8 test tubes. Well, wait a second. 3 sig figs, 1 sig fig. Do we round to 1 sig fig? No, because the 8 test tubes doesn't mean approximately 8. It might be 7.97 test tubes. You can't have a 0.97 test tube, right? So you count 1, 2, 3, 4, 5, 6, 7, 8 test tubes. We're only going to go off of this number in that calculation. Does that make sense? So if you get something by counting, I count out 8 test tubes, or a definition, don't even worry about those numbers in scientific or in sig figs, because they don't affect the outcome of our answer, the rounding. Questions on that? Does that make that rule a little bit more clear than it did the first time I explained it? All right. Now, when it comes to actually doing the calculations, sometimes, as I mentioned a moment ago, we base our answers off of the place value. Sometimes we base it off of how many sig figs. For instance, in some cases I'd say 3 sig figs. In some cases I'd say tenths place. When do I do what? Back to Kendall.
You go off of like the place value for addition and subtraction.
Good. If you're adding and subtracting, then when you do your calculation, you're going to worry about the place value. Whatever number in the string has the least significant place value, that's what you round to. So if I had something like a 7.13, and I have a 250, and I have a 12.7, and we're going to add these numbers together. Well, when I get my final answer, I'm going to round it off to which place value, class? The tens place. Because this number was rounded to the tens place. This was hundredths. This was tenths. Well, those are more exact. This is the least exact number. I mean, seriously, 7.13. You know, I mean, if you were, for instance, doing, thinking back to your PE days, right? 50-yard dash, right? And you finished in 7.13 seconds. That's a pretty detailed time, right? If you're talking to mom, you may or may not, you might say, yeah, I ran it in 7 seconds, right? 7.13, that's what the stopwatch gives. Or 12.7, that's still pretty exact. 250 very much sounds like we're approximating, doesn't it? Since this is the least significant, that's where we would round, is to the tenths or the hundreds place value. Does that make sense? Same with subtraction. We would round to whatever place value seems to have the least exactness or least significance. So therefore, with multiplication division, Michael, what's the rule?
I know it, but I don't.
I can't articulate it at this time. It's a Monday morning. Of course you can. Let's see if Audrey can articulate on a Monday morning. Kendall, to the rescue.
Like a number, you look at the number and like see how many sig figs in?
Yeah, but for instance, if I were multiplying 7.13 and 12.7 and 250, if I'm multiplying them, I don't care anything about place value. 3 sig figs, 3 sig figs, 2 sig figs. I'm going to lock in on whichever number has the least significance based on the number of sig figs. For instance, if I had a 7 here, 7, 12.7, 250. Well, if you were looking at place value, you'd say this is less exact. But if you're looking at number of sig figs, this only has 1. So my answer is only going to have 1 sig fig, because that's the least amount of sig figs in any given number. Does that make sense? Unless, of course, the 7 was obtained by counting, or by definition, like days in a week. I'm not using 7 as a significant, because that's 7.00000, right? It's an infinitely significant 7 if it's days in a week. Or if I counted 7, masses that I put onto a scale. Okay, well that's, or pennies, for instance, in a science project. Well, that's counting. That's infinite significance, right? But if it's just 7 approximately, it took 7 seconds to finish. Okay, well that wasn't by counting, that wasn't by definition, 1 sig fig in the answer. Questions on how to round based on sig figs. Does that make sense there in that review? All right, so we're going to actually use, one more thing I wanted to talk about, and that was when we can add and subtract, multiply and divide different quantities together. For addition, subtraction, remember, if I'm trying to add together a couple things, for instance, I wanted to add kilograms plus some number of meters. How does that rule work out? Audrey?
You have to see if you can do it first.
Okay, can I? No. Because kilograms is mass and meters is length. You can't add mass and a length together, right? Could I add kilometers and meters together? Yes, but
You gotta change one.
yeah, I'd have to make them both kilometers first, or both meters first, right? Same with subtraction. They have to be the same kinds of things, time and time, mass and mass, whatever. And they have to have the same units. What about multiplying? Could I multiply grams in kilometers, class? Yeah. But in my answer, what's the unit going to be for my answer, class? Grams times kilometers, right? I can't think of that time we'll actually do that, but theoretically you could, right? You could multiply just grams times kilometers. What about dividing? Could you divide grams by kilometers? Yeah. What would you get for in your answer as your unit then, Audrey?
Grams over kilometers.
Grams per kilometer, right? Or grams over kilometers, right? Could I divide grams by kilograms, class? Yes, but, Kendall, Audrey?
You have to change one of them.
Yeah, I gotta make them both kilograms or both grams so that for your answer, what unit would you get, class?
Kilograms.
Nothing. Kilograms over kilograms would cancel away, remember. What about multiplying? Could you multiply grams and kilograms, class? Yeah, but
You have to change.
gotta make them both grams or both kilograms. So what would I get in my answer?
Grams squared.
Grams squared. Because grams times grams is grams squared. Grams divided by grams, grams cancel. Okay, questions on that? It feels like a Monday, doesn't it? All right, well, let's practice with a little of these units as we do something called dimensional analysis. Remember, the key to dimensional analysis is using fractions to get rid of units, cancel units as you put units over the same units. All right, and so let's start with something like 12 miles per hour. Okay, this is a pretty brisk run, not quite a dead sprint, but a brisk run. And if somebody were running 12 miles an hour, how many meters per second would that be? All right, so remember the key to dimensional analysis here is to start by writing your given value, the 12.0 miles per hour, writing it, class, as a fraction. How would I write it as a fraction, Kendall?
12.0 miles over 1 hour.
All right. And then we're going to multiply by a series of ratios. Now, every fraction we multiply has to equal 1. By making sure that whatever we have at the top and whatever's in the bottom are the exact same. They'll look different, but they'll be worth the same. For instance, if I wanted to get rid of hours and I wanted to change it into seconds, well, Well, I know how many, or should know, how many seconds are in an hour, Audrey?
3,600.
3,600. So I'm going to multiply by what ratio?
1 hour over 3,600 seconds.
Good. 1 hour over 3,600 seconds. And that allows the hours and hours to cancel. For instance, I don't know how many meters are in a mile. But I can change my mile into, Michael, feet. Because I know how many feet are in a mile.
5,280.
So I'm going to write.
5,280 feet in 1 mile.
Now, how did you know, like Audrey put her hour on top and her seconds in the bottom. You put your feet on top and your mile on the bottom. How do we know?
Miles has to cancel.
Right, since this miles is in the top, the other miles has to be in the bottom, so they can cancel with each other. And now I've got feet over seconds. I want meters over seconds, Kendall. So how do I go from feet to meters?
There's 3.281 feet in a meter.
Good, that's a number we need to memorize. There's approximately 3.281 feet in a meter. So we'll write
1 meter, 3.281.
Now, of these numbers, 2 of them are definition. 1 of them is not. Which one is not a definition number, class?
12 miles.
Well, okay, the 12 miles, sorry, that was given. Of the 3 units we used to multiply, 1 of them is not a definition.
3,600 seconds.
That is definition, actually. That is exactly, like, infinite significance, 3,600 seconds in an hour.
3.281.
The 3.281 is an approximate, right? We don't define the meter as 3.281 feet. It just is about equal to that. So I'm not concerned that there's 2 sig figs here. There's not. There's infinite sig figs here. There's not 3 sig figs here. There's infinite sig figs here. But here we have 4. And here in the given number, we have 3. So when we get our answer here in a moment, class, how many sig figs in the answer? 3. Because there was multiplication and division that occurred, we're going to go off whichever number has the least significance. That's this one. So remember, on your calculators, you'll multiply all of that across the top. And then remember, you can divide by the bottom. And then divide by the bottom again, rather than multiplying the bottom and then dividing. It saves a little bit of time. So the 12 times the 5,280, divide by the 3,600, and then also divide by the 3.281. How many meters per second is this person running? Class?
5.364.
Good. 5.364 ... So when we round our answer to 3 sig figs, class, we'll say
5.36.
about 5.36 meters per second. All right, questions on this? Questions on this? All right, the last thing that we want to cover in this first chapter, this introduction, if you will, to just basic scientific mathematical stuff, is throughout the year, we're going to deal with fractions quite a bit. And we want to make sure we know how to handle fractions when they come. So I want to review some things from algebra with you. One of the things we saw in algebra was something like this. If I had like 2/3 x. You remember with something like 2/3 x, when you were in algebra, I said the best way to write this is to take whatever is at the end and just move it up to the numerator. So that this would become, Audrey, 2x over 3. In general, you could write this in your notes. A over b times c could be written ac over b. If something comes after a fraction, being multiplied, of course, then just move it up to the numerator. This is going to be true as well if, for instance, you had an a and then you multiplied it by a b over c. If you had a whole value multiplied by a fraction, well, still, if it's a whole value multiplied by the fraction, you just move it up. So that a times b over c, Kendall, would become ab over c. Okay, stuff from algebra that you should remember. Any questions on it, though, as we start the year? We're going to see this somewhat frequently. Fractions and whole values. Again, if you move it to the numerator, it just makes your life easier. Another thing you'll see this year are complex fractions. That is, fractions with fractions inside them. Like here, my numerator is a fraction a over b. My denominator is a c over d. Going back to algebra class, what is a complex fraction really? Anyone? What does a fraction bar mean? So then a complex fraction is really just a division problem, right? But do we ever divide fractions? What do we do, Michael?
Multiply by the reciprocal.
Multiply by the reciprocal. So this is going to become A over B times the reciprocal D over C, which means it then becomes AD over BC. So put this in your notes as well, just as a reminder to yourself of how to work with complex fractions when we see them. Don't let them throw you off, don't let them bother you, just roll with it. Another thing that we'll see throughout the year talking about fractions are two fractions that are equal to each other. What do we call two equal fractions? Well, technically, yes, it's an equation, but it's a special kind of equation. It's a special name. A fraction equal to another fraction. A proportion, right? So if you saw something like this, A is to B as C is to D. If you were to see a proportion, remember how we solve proportions, class? Cross multiply. So if you were to have this proportion, A is to B as C is to D, we would simply cross multiply. We'd say that the product of the extremes, class, AB, equals the product of the means, BC. We remember cross multiplication from past classes. Now, another thing, and Michael, you're just now taking geometry, so here's something you haven't seen yet. You two should remember this, but it's been a little while. And that is a transformation, Kendall and Audrey, that we did in geometry called the alternation transformation.
Audrey is needed in the chapel.
Right now?
Yeah.
Oh.
Can you what?
All right, so the alternation transformation, here's basically how the transformation works, Michael. Since we would solve a proportion by cross multiplying, since A is to B as C is to D becomes the product of AD equal to the product of BC, if I were to flip-flop these two numbers and get D is to B as C is to A, do you see it would still equal the same thing when you cross multiply? Because multiplication is commutative, then an A here and a D here is no different than a D here and an A here. Or you could flip-flop these two values. Because again, they're still going to give you a BC even if they traded places. So you could say A is to C as B is to D. Because it would still give you the same cross-multiplied products. Does that make sense? We call this, again, alternation, if you'll make sure you have that in your notes. Kendall, do you remember this from geometry class? You're going to use this transformation a bunch this year, and I'll show you where you're going to use it. Write this down in your notes. Anytime the variable you want is in a denominator, if the variable you want is in a denominator, alternate to get it out. If the variable you want is in a denominator, alternate to get it out. If a variable you want is in a denominator, alternate to get it out. For instance, you might remember doing problems like this back in the past. A is equal to B over C, and you were told to get the C by itself. Well, back before the days of geometry class, before learning the alternation transformation, you had to multiply both sides by C and then divide out. Yeah, it was a two-step process. Nothing wrong with it, it works. But watch how it would be quicker. You ready, Michael? Okay. If you put the A over 1, you've just made a proportion. And if you simply alternate these two values, you now have the C over 1, I don't care about the 1 anymore, and you have the B over the A, and boom, the C is by itself. So in one easy step, you get the letter by itself that you want. So if the letter you want is in a denominator, alternate to get it out. And we're going to practice with that a good bit here today. Now, let's also then, as we build off of this idea of working with fractions, working with these letters, let's also look at some literal equations. And you read about these two things in your homework reading, I believe, over the weekend. Literal equations. Remember, a literal equation is just an equation with letters instead of numbers, right? Instead of a single letter, there's lots of letters. Basically, formulas. And we worked with these quite a bit in Algebra 1 and Algebra 2. So let's take a look at some basic literal equations that we might see throughout the course of this school year. For instance, write this down in your notes if you would. F equals ma. This is the basic equation for force. Force is the product of mass and acceleration. Well, supposing I wanted to solve the equation for m, meaning I wanted to get the m by itself. Well, what would I have to do to get the m all by itself, Kendall?
You can divide by 8.
Just divide both sides by a. And when I do, I get m is equal to
F over 8.
f over a. Do you remember doing this in algebra class? All right, write this one down if you would, please. D is equal to 1/2 gt squared. D equals 1/2 gt squared. This is used to calculate the distance of an object that begins falling in free fall. All right, let's suppose we wanted to solve for the time here, the letter t. Well, notice, first of all, we got a fraction. I hate fractions. They complicate things. Do you remember from algebra class how to get rid of a fraction?
Multiply by 2.
Well, in this case, yes, but in general, multiply everything by the LCD. So we're going to multiply everything, which is these two things, by 2, which is the LCD. Now here, the 2 we multiply by cancels with the 2 denominator, leaving with 1 gt squared, or since I'm lazy, gt squared. And on the left-hand side, 2 times d, 2d. So far, so good. We remember this from algebra. Now, how to get the t by itself? Well, let's start by getting rid of the g. How would I get rid of the g, Michael?
Divide by 2.
Divide away the g. And now I've got the t squared equals 2d over g. But that's t squared. I don't want t squared, I wanted t. How do I get rid of a squared? Kendall?
Take the square root.
Take the square root. And what you do, one side of course we'll do to the other side as well. So that'll give me t is equal to, now careful, whose idea was it to take the square root? Kendall's. Ours, collectively, right? So we got to remember to put a positive negative on our radical. Now, in this case, we'd be talking about time, right? Can you have negative time? Not really. So in this case, we would ignore the positive negative, but technically, since that won't always be the case, remember when you take a square root, don't forget positive negative. Questions on this? Again, remembering this from from algebra class in years past. All right, write this one down. D is equal to V sub I t plus 1/2 a t squared. By the way, notice how I read this. D is equal to V sub I t. You would say sub to indicate a sub notation. It's like the opposite of an exponent. An exponent goes up, a sub notation goes down. Sub notation is going to be used a lot this school year, especially with some things like forces. Right? There's all kinds of different forces. There's tension force, normal force, applied force, centripetal force. You see how I just use little subnotated letters to specify what I mean? Well, that's what we see here. V sub I refers to a velocity, refers to an initial velocity. You don't have to know that yet, I'm just saying it, okay? But let's suppose I wanted to get this A right here by itself. Well, first things first, I see a fraction. And I hate fractions. So Kendall, what should I do?
You multiply anything by LCD.
Everything. This. All three things, all three terms by the LCD, which is just 2. When I multiply everything by 2, what do I get, Michael?
2d equals 2d sub I t times at squared.
For plus at squared. Good. And now the fraction's gone. Now, to get the a by itself, what do I need to get rid of next, Kendall?
The 2v sub IT.
Good. Remember in algebra we said get rid of the least attached thing first. Now fractions, I just like to get rid of right off the bat because I hate fractions. But I'm not going to get rid of the t squared yet. It's attached to the a. So quick refresher from algebra. Let's move the 2v sub it over and just get rid of it, making it a. So on the left side now we should have
2v minus 2v sub IT equals AT.
There we go. And now the only thing left to get rid of to get my a by itself is the t squared. How do I get rid of the whole t squared just in one step, Michael?
I'm not
we actually don't need a square root to get rid of a t squared. I would need a square root if I were trying to get the t. I can just divide it away. But remember, what you do to one side, class, do to the other side. So the entire side gets divided by t squared. So not each term, but this gives me a is equal to 2d minus 2v sub it all over t squared. Does that make sense? All right, again, this is an equation we'll see later on this year. Here's another one. Lambda equals c over f. Lambda equals c over f. Talking about the wavelength of electromagnetic waves here. And supposing I wanted to get the letter c by itself. Well, what would I do to get c by itself, Michael?
Multiply by f.
Yeah, multiply by f. Of course, what we do to one side, we do to the other side. So that'll give me c is equal to...
Lambda divided by f.
Oh, careful. You said multiply by f, right?
Oh yeah, lambda
So,
times f.
Lambda times f, or just lambda f. Makes sense? All right, how about this one? R equals V over I, talking about resistance in an electrical circuit. And supposing I wanted to get the I by itself. Suppose I wanted to get the I by itself. What would I need to do here? Well, it's in a denominator. And if it's in a denominator, class, how do I get it out? Alternate it out. Think of the R as R over 1. And then just alternate these two extremes. What would that give me, Kendall?
I equals R over...
Ooh, careful.
V over R.
Good. The V doesn't move. It's the R that now takes the bottom spot. And in one easy step, we're done. In years past, before geometry, you would have had to multiply both sides by I and then divide away the R. And you would have still got the same thing. It's just quicker to alternate now that we know that. Take a look at this one here. This is a little bit more complicated. T equals 2 pi times the square root of m over k. This is an equation we'll use later to talk about the period of a pendulum in motion. And t equals 2 pi times the square root of m over k. Let's suppose I wanted to get the k all by itself. What would I need to do first? What do you think, Audrey?
Square the square root.
Well, I don't have the square root isolated yet. Remember when we talked about radical equations in algebra, we said isolate the radical, then square both sides. So you're right, at some point we will, but let's isolate the radical first.
Divide by 2 pi.
All right, on both sides, divide away the 2 pi, so that on the left-hand side, I've got t over 2 pi, and on the right, it's just an isolated square root of m over k. Now we will
Square the square root.
square both sides, right? And so when we square a square root, class, we get the radicand. Good statement I've memorized from algebra. Square a square root, you get the radicand, which of course in this case, Audrey, is
M over k.
m over k. What about on the left-hand side? What do we get when we square that fraction, Audrey?
T squared 4 pi squared.
Good, t squared over 4 pi squared. Now here's the key. Now I'm ready to get the k by itself. I had to clear away the 2 pi. I had to clear away the radical. And both of those things are done. And what I'm looking for, class, is in a denominator. And if what I'm solving for is in a denominator, how do I get it out of there, class? Alternate. Michael, what will I get when I alternate the k out of the denominator?
K over 4 pi squared equals m over 2 squared.
Good. Now, only one step to go, and that's finish getting k all alone. How do I finish getting k all alone, Kendall?
You can multiply by 4 pi squared.
Right, multiply the 4 pi squared on both sides. And remember, if it comes after a fraction, we put it in the numerator. So Kendall, what is k equal to?
M 4 pi squared.
Well, remember, we put constants first. So the 4 is a constant. Technically, pi is a constant as well. So we'll put 4 pi squared m all over t squared. And again, these are just some examples of some literal equations of how you to rearrange to get them all solved for the letter that we want. And I believe this is what we did in the homework. So looking at page 18 with me now in your textbooks. And we're finally, now that the class is almost over, we're going to look at the homework that you did. Now you may realize as we're going through here, oh, I didn't do that correctly because I've forgotten some basic algebra. That's okay. We'll correct it as we go. Taking a look at number 14. We started with the equation PE equals 1/2 kx squared. Looking at the elastic potential energy here. And again, you don't have to know what these equations mean yet. I'm just giving you a preview of how we're going to use some of these things. We wanted the x by itself. Audrey, on 14a, what did you do?
I divide by 1/2.
Well, do we really divide fractions? No. So really what you did was you
Multiply
by
2.
2. And if you do that on both sides, you'll get
2 PE equals K times X squared.
there we go. All right, still trying to get the x by itself. Then what would we do?
Divide by the K.
Divide it with a k. I'm going to be lazy and do it like that. And then what will we do?
Use square root the X.
Take the square root of the x squared, and the square root cancels with the square, and I'm just left with x. But what I do to one side,
Do to the other.
so on the other side, I'm also going to take a square root of 2pe over k. But when I take a square root, I need to remember to put what, class? And this would need a positive negative because the x is referring to possibly stretching or possibly compressing or squishing. And depending on whether it's positive or negative, that makes a difference. So we would need the positive negative there. Did anyone have this for 14a? Anyone have this but maybe forgot the positive negative? Okay, questions? Does it make sense now? Even if it didn't before, I gave it to you knowing we might not get them all right, but I wanted you to at least put some thought into it. I was curious to see how we do. Does it make sense now? All right, that's the most important thing. The next one is the law of levers, which we'll get to later. F sub I, R sub I equals F sub O, R sub O. And we want to get the R sub I by itself. Kendall, pretty easy here.
Divide away that F sub I.
Yeah, just divide it away from both sides to get what for our R sub I answer.
F sub O, R sub O over F sub I.
There we go. Pretty straightforward. I think we all should have had letter B correct. Good. Letter C. Now here's where if you didn't know about the alternation, it was annoying. But if you do know about alternation, it's pretty easy. The key is to think of the F class as being F over 1. Now you don't even have to write the over 1. I will just to show it, but you don't have to write it, but you have to at least think F over 1. That way I can alternate this extreme with that extreme, and in one step, Michael, I've got
R equals, let me see, that's F times F MV2.
oh, careful. If I alternate these two things, I trade places with them.
MV squared over F.
There we go, mv squared over f. Did anyone have that last night? Okay, no one did. Does it make sense now? Now again, the old-fashioned way is to multiply both sides by r to get fr equals mv squared, and then divide away the f from both sides. And you still get the same answer, but the alternation is quicker. It eliminates the need for two steps. And hey, if we took the time to learn it in geometry, you will. You'll actually be ahead, so just don't tell the rest of the geometry class, you already know it. But if you took the time to learn it in geometry, we might as well use it, right? Be lazy mathematicians. Questions on this? All right, let's take a look at the next one. We have a v sub f is equal to v sub I plus at. And solving for the t here. And we're back to Audrey. What do we need to do?
You can subtract the VI.
Good. Or we could say move it over. Either way, technically, yes, you're subtracting it to get.
VF minus VI equals AT.
Good. And we say that v sub f minus v sub I, the subnotation for a final velocity and an initial velocity. And again, still trying to get the t by itself, so now just divide away the a, and again, the lazy person in me is going to do that right there, and there's our answer. T equals v sub f minus v sub I over a. How many have that for your answer? Good. Again, just key is to get rid of the least attached thing first. The next one's really easy. Rotational inertia, I equals mr squared, and trying to get the r by itself. Kendall.
Divide away the A.
Okay.
And then you take the square root.
But when we do,
Positive.
and how many have r equals positive negative square root of I over m? And we have it just without the square positive negative? All right, questions. All right, and then the last one is, erasing to myself a little room here. V sub f equals the square root of v sub I squared plus 2ad. And we're trying to solve for displacement here. And Michael.
Square. Yes.
Square, technically both sides, but yeah, when you square the square root, you're just going to get the... When you square root, you get the radicand, right? So it just cancels away, so I'm left with this, right? And then over here, of course, I got the VF squared. So VF squared equals VI squared plus 2AD now, all right?
Subtract V sub I squared.
Good, subtract it away. That's lazy man's way of doing it. And then,
Divide 2A to both sides.
and there's lazy man's way of doing that. And so we get D is equal to VF squared, V sub F squared minus V sub I squared all over 2A. And how many had that for letter F? All right, questions on this. I take a few moments to do number 16. Number 16, solving for the bolded portion. On one of them, they have a KE. That's collectively one thing. So it's not a K and an E. KE is thought of as one item, kinetic energy. Just another minute or so. Go and check your answers. By the way, this is omega. It looks like a W. This is alpha. So a couple of Greek letters will be used throughout the year on occasion. How'd we do? Out of 6, how many? Anyone go 6 for 6? You got all of them correct. All right, 5 out of 6. Just missed one of them. Okay, Kendall, which one?
That one. The third one.
The third one right here. So multiplying the 2 to clear off the half, dividing away the m, and then taking the square root. All right, Michael?
The second one, I got WF plus alpha T.
Okay, so remember it's a positive alpha T and a negative omega sub I. What I did was I pulled a double switch, right? Since this is negative, I didn't want it to stay negative, so I moved it over as the positive, which moved the positive here over as a negative. So that double switch from algebra class. Good. Audrey, which ones? Of the ones you did, how did you do? All right, your homework for this evening. You're going to practice with one more set of these. Page 18, problem 15. Page 18, do problem 15. Study pages 9 to 16. Study pages 9 to 16. So do page 18, problem 15. Study pages 9 to 16. And then to preview what we're going to talk about tomorrow, read pages 19 to 23. Read pages 19 to 23. And 4 questions for you to answer on page 31. Page 31, answer questions, not problems, questions 1 through 3 and 13. Page 31, questions 1 through 3 and 13. All right, we'll take a look at all of that tomorrow. Have a wonderful rest of your day, and you are dismissed.